Welcome to Special Relativity. Special Relativity is the brainchild of Albert Einstein. A little bit of history here. He was born back in 1879 in the German Empire. In about 1940, he moved to the U.S. Because of the war, and he lived here until he was 76 in Princeton, New Jersey. So in 1905, Einstein was 26 and he worked for the Swiss Patent Office. He reviewed patent applications, mostly having to do with electrical machinery and things like that. But that was his job. He wasn't an academic in the classical sense. He didn't have an academic job. But he did form a club with some friends who are all, like him, very brilliant when it came to mathematics and science. They called it the Olympia Academy. And they sat around and they discussed physics and they discussed mathematics. This was their fun time, if you will. And out of that, in 1905 came four papers in a collection called the Annus Mirabilis papers. So what are they? They were on a heuristic viewpoint concerning the production and transformation of light, on the motion of small particles suspended in stationary liquid as required by the molecular kinetic theory of heat, on the electrodynamics of moving bodies, and does the inertia of a body depend upon its energy content. So to cover what these actually are, the first one is all about the photoelectric effect. And the photoelectric effect was the first hint we had at quantum mechanics, in which Einstein proposed that light was actually quantized. Small particles suspended in a stationary liquid was all about Brownian motion. And again, this had to do with quantum mechanics at some level, but mostly having to do with the application of statistics to large number of particles. So here, in some sense, we have one, the birth of quantum, and two, the birth of statistical mechanics or statistical physics, these days called condensed matter physics. The third one was was relativity, special relativity. Not special relativity, which we're going to cover, or at least in some sense, in this lecture. And then the fourth one was where he gets to his famous equation E equals mc squared. So here he is. He's working in a patent office. He has a job that keeps him busy all the time. For fun, he goes out and plays with physics and math. And his first sort of entry into the academic world after his schooling was to shake the foundations of physics as we knew it. And this picture is a picture of Einstein of about the age of 26. This is a picture of Einstein as you probably have seen it before. This is the Einstein that had been at Princeton for a while. So now we're getting into Einstein's postulates. So his postulates start with an inertial frame of reference. So an inertial frame of reference is a reference frame in which a body at rest remains at rest and a body in motion moves at constant speed in a straight line unless acted on by an outside force. So an inertial frame of reference, all of us exist in our own inertial frame of reference, but you can also imagine if you are in a moving train car, you're also in an inertial frame of reference. All right. So Einstein's first postulate was really to answer some of the very bizarre things people had begun to construct to explain some of the phenomena they were seeing. His first postulate was the laws of physics are the same and can be stated in their simplest form in all inertial frames of reference. Now, this was simply Einstein imposing, in some level, his own aesthetics on physics, if you will. But it turns out to be true that the physical laws that everything obeys should not depend upon whether or not you are standing on the train platform or riding along in the train car. They should be the same. That's basically what he's saying. His second postulate comes from some Michelson-Morley experiments. And this has to do with how we thought light was transmitted. We thought light was transmitted through the ether. Um, that essentially the universe was made up of this stationary set of tiny little spring-like things that gave us the transmission of light, of electromagnetic waves, because, you know, all other waves had some medium in which they were transmitted. So they were making up a medium for light to be transmitted in. Well, if light is transmitted in a medium, then, if you imagine you've got the sun, you've got the earth going around the sun, right? If light's transmitted in a medium, then if you measure very precisely how light travels in a path as you send it around what's called a Michelson interferometer, right? So they would bounce light around in different directions along very precisely calculated paths so that they were exactly the same. And then they would look to see, was the light in phase or out of phase? Did it add or did it subtract when it got back to where they wanted to measure that? And what they found was that it made no difference what time of year it was, where the motion of the earth was, what time of day it was. Can't imagine if you're imagining there's an ether here, throughout the day and throughout the year, you're traveling through it, right, in different ways. And the earth moves at a significant speed, right? Earth moves at a pretty good clip through space. So, they were just looking at, can we detect the fact that we're moving through this ether? And the answer was a resounding no. In some ways, their experiments completely failed in that they did not find at all what they were looking for. On the other hand, it led to Einstein and his second postulate, which is the speed of light, c, is a constant independent of the relative motion of the source. This is a big one, and it has a lot of implications. All right? Speed of light is a constant independent of the relative motion of the source. So if I'm running at you with a flashlight shining at you, the light coming from the flashlight doesn't get added, and the speed of light coming from the flashlight doesn't get added to my speed. It's not the speed of light plus how fast I can run. Let's be generous and call that 5 miles an hour at the moment, right? And if I'm running away from you and you're shining a light at me, the light isn't hitting me at less than the speed of light, it's still hitting me at the speed of light. So the speed of light doesn't depend on our relative motion. It is always a constant. So, special relativity, which is what we're looking at here, differs from general relativity in one very big point. Special relativity does not in any way take into account acceleration. So it applies only to unaccelerated motion. We might talk about acceleration, we might talk about some of the things that happen with respect to that, but there are, and I may discuss them at the end of all of this, there are several paradoxes that occur in special relativity that aren't really cleared up until you get into general relativity. General relativity was also Einstein's invention, and general relativity is where he began to see gravity as a geometrical change in space and time. So the general relativity is it's not really for this course, but general relativity is where he finally cleared up some of the paradoxes that we could discuss in special relativity.